Can anyone hear me?
Copy.
Okay, good. Great. We'll wait one more second. Josh, what's your question?
Oh, sorry, I didn't have a question. I was trying to get the thumbs up one.
Oh, okay. Well, welcome everyone. I know it was a crazy weekend, crazy week with the exam and everything. We're going to start some new stuff today. I think it's kind of exciting. I got a few demos and got some pictures that we can look at. We're going to talk about heat exchangers today. We're going to spend several days on heat exchangers. And if we need to change some of the stuff we need to do at the end to make sure everyone's settled on these, then we can do that. Let's go ahead and start with the prayer. I'll say it just because that way you guys don't have to unmute or anything. Father in heaven, we're grateful that we can begin this class with prayer. We're grateful that we have this technology that can help us to teach and learn even when we are far away from each other. We pray that that would bless us with an extra measure of the Spirit so that we can be edified and learn and rejoice together. We pray for those who are sick that they can get better. We pray that that would slow the spread of this virus and that it can get contained. And we pray mostly that we can be patient and trust in thee and in thy time frame. And we say these things in the name of Jesus Christ. Amen. Okay. I'm going to start first by showing you some pictures on these PowerPoints about some heat exchangers. And we've talked about heat exchangers before. Here's finned heat exchangers. We've talked about fins. We've done fin efficiencies. We've done resistances with fin efficiencies. And we do this to increase the heat transfer on one side of the heat exchanger, basically the air side or the vapor side. We have these because we like to transfer heat with air because it's cheap. We can put these outside, we put them on our car, but because air is a bad conductor of heat, it has a bad Prandtl number, so to speak, it has a low Prandtl number, then we have to up the area, because H is so small relative to, say, fluids or liquids. And so you just see some various examples here. Down on the right, you see some, like, it's basically just a pipe with fins on the outside. It's called a finned heat exchanger. Well, all of them are finned heat exchangers. Or you can have banks of tubes like you see with your car radiator on the left. You have one fluid, usually the hot fluid is going through the tube, and then the colder fluid, the air, is on the outside, and you can blow across it, or it can be free convection. There's another heat exchanger called a brazed plate heat exchanger. These are made by putting a lot of different plates together, and then you have a little gap between each plate, and the hot fluid flows through one gap, and then on the next gap, it would be the cold fluid, and you alternate hot and cold, and you can kind of see that in the picture on the right. And I put a lot of these plates together, and I have what's called this brazed plate heat exchanger. Brazed is what we mean when it's like welding. They're not necessarily welded because of the different materials, but they are soldered or welded. They're bonded together. I've actually got a cutout of one of these brazed plate heat exchangers. And so we just cut it diagonal down. It has 4 ports. You don't see the fourth one or anything of the fourth one over here. One would be the inlet for the hot stream. One would be the outlet for the hot stream, the inlet for the cold stream, the outlet for the cold stream. And I can swap them. I can do counter or co-current. We'll talk more about that. You've probably heard those terms before from 273. But you can kind of see how every other plate is hot, cold, hot, cold, hot, cold. These have really great H's. They have great H's because those gaps are so small that you get really good contact between the hot and cold. The challenge with these is they have very high pressure drops. And so you have to design your pump to drive this system pretty big. They also can't be cleaned very easily. You notice we had to actually cut this thing apart to actually just show you. We couldn't show you the middle because they're kind of brazed together, they're bonded together, so you can't clean them very well. Heat exchangers, some of the others we'll talk about, you can clean. You could clean it chemically, like run an acid through there if you got some sort of hard water buildup. Brazed plate heat exchangers, they're very cheap also. Like one of these, a lot of people in doing their own biofuels at home or whatever have these for their heat exchangers. This one was probably like $12 or something like that. Bigger ones might be up to 100 versus a shell and tube heat exchanger, which big ones can run up to the hundreds of thousands of dollars. Let's talk about something that's very similar to a brazed plate heat exchanger, a plate and frame heat exchanger. It's the exact same principle, except instead of bonding or brazing them together, you put a gasket between each level, and then you crank it down with those big bolts you see so that it doesn't leak. And that's the big challenge with these. They're made so that you can clean them. Theoretically, you can take them apart and then mechanically clean off any gunk that's in there or any things that might be clogged up, but they leak like crazy. They're very hard to make them so they don't leak. And they do also suffer from the same thing that brazed plate heat exchangers do. They have high pressure drops. You get good H's, but the trade-off is pressure drop. So let me show you now kind of the standard. Oh, one more before we get to shell and tube. A concentric tube heat exchanger. This is probably the simplest heat exchanger you can think about. I take a pipe and I put a bigger pipe around it. And so one fluid flows through the inside and one fluid flows on the outside of the inside tube, between the inside tube and the outside tube. We call that the annulus, or the annular region. And you can kind of see how we can do that. These are very easy to analyze, and they're used in a lot of different cases, especially older things. They're not as expensive as shell and tube heat exchangers. They do suffer also, though, from getting, it's not easy to clean the concentric part. I could shove some sort of mechanical thing, kind of like you would a giant bottle scrubber, through the inside tube to clean it out, but I wouldn't be able to get the outside tube very easily. We'll talk more about parallel versus countercurrent in a minute. And then finally, shell and tube heat exchangers are probably the most ubiquitous heat exchangers out there. I've got an example right here, and I've got it so that it's cut away. And what you see is basically you have a bunch of tubes inside a shell. And if I turn this on end, you can see that the tubes are not going to pass fluid through the shell side. You only get to go through the tube side. And then I have to go through, you probably can't see too well, but down this entry here into the shell side, it's on the outside of the tubes. So you separate the fluids. The shell side fluid is separate from the tube side fluid. If one's hot and one's cold, you'll transfer heat. These things right here that you can kind of see are cutting off part of the tubes, maybe about 2/3 of the way through the shell. Those are called baffles. And we do that to just make the flow go back and forth and increase H, make it more turbulent. That does increase pressure drop, but you want to, so there's a balance. If I put these really close, then it's a really high pressure drop. If I put them further away, it's a lower pressure drop, but I have less heat transfer. So there's a balance that we make here. And you can kind of see that on this diagram right here. And so you can see the shell fluid comes in and it goes back and forth around the baffles, and then it would come out the other side. So here would be a shell inlet, here would be a shell outlet. And you can choose which one's inlet and outlet. And then the tube side, you can see this is called the bonnet, the thing that you screw into the tube, the pipe, that your entrance pipe. And then this one, we took the bonnet off so you can see the tube bundle. Then it just comes through, and let me move this real quick. It comes through, the tube inlet goes through all the tubes and then comes out. And designing how many tubes are in your tube sheet, how close they are, that is all sorts of design things that you can consider and that people that make heat exchangers have considered for you. You can design them however you want. This one was just bought off the shelf. We go through a company called Standard Exchange. We've bought several heat exchangers over the years from them. It's a company that's absorbed a lot of other shell and tube companies, but there's different ones that sell them. And if you buy one off the shelf, it's cheaper than if you get a custom made one. But they all work on that same principle, a tube bundle and a shell. So I'm going to pause right
Shell
here.
and tube companies different than shell companies.
No, usually the tube they sell the whole thing. And we'll talk in a couple days about different types of shell and tubes. This one has what's called a fixed tube bundle. I can't take it out. It's welded onto the shell. There's some so that I can clean the shell and the tube where you can actually pull the whole tube bundle out. And I'll show you pictures of that in a couple days, where you can clean the outside of the tubes and you can clean the shell and you can clean the inside of the tubes. And so it's usually the same company. You can search them up. Standard Exchange online. We do that in UO Lab, and it's not EX. They kind of be fancy. It's Standard X, capital X Change. And I think their parent company is called Xylem or something like that, because they've absorbed several other companies. That's a big heat exchanger company though. Do you guys see these, see this thing I'm moving around, or is that only me that sees it? Or do you just see my PowerPoint right now on the screen? Anybody?
We just
I think it's just the PowerPoint.
Okay,
Dr.
good,
Mo.
because I see a bunch of your pictures. I just want to make sure I'm not covering something up. Okay, now there's something else I want to tell you about heat exchangers, and we'll review this in just a second, is you get what's called fouling. Fouling is basically just junk. I have an example of that. Here's a heat exchanger. It's about 2 feet long. It's in our UO lab. We actually took it out. It's one we had in our UO lab, and I kept it around just for to give an example. American Standard, you can see that company that we bought it from is what Standard Exchange used to be called. This was like 40 years old. But if you look at the tube bundle, so it's sitting like this. If I look and show you the tube bundle, then you're going to see there's a bunch of junk right here on it. See all these hard water deposits compared to the other side where there's fewer, you kind of still see the bare metal. That is what's called fouling. It's basically just junk that builds up. Now, someone tell me, if you have junk building up, what happens to your heat transfer?
Decreases.
It decreases. It's another resistance. It's a level. It's a conduction resistance that's getting deposited onto your tubes. And so fouling is a huge deal. When you go into industry, you want to know how much fouling you have. And what you'll probably do in industry is you'll track the heat transfer over time. And then you'll say, once it gets to this level, I got to take it offline. And once it decreases a certain level, I'll take it offline and then clean it out. And then you'll have a secondary heat exchanger that you'll run while you're cleaning that out. And so fouling is a huge thing. It greatly reduces heat transfer. You're going to hear that term. We quantify it with something called a fouling factor. And if we knew what this junk actually was, you could, and how thick it was, you could just do a normal resistance, right? Log R2 over R1, 2 pi KL. But you don't know what the K is, you don't know what the R is, and so we just kind of lump it together and call it a fouling factor. And we'll show you how to do that in a minute. But you'll notice that this one that was in our UO lab for like 40 years, some of these tubes are actually almost totally closed off. This had a very high fouling factor. You can kind of see this one has a bunch of junk in it on the other side that's coming out. Let me see if I can, there we go. There's that little bit of flake that's come off, but you can clean. These are hard water deposits because we just run typical water from the city on the tube side. Same thing probably happens in your apartments or your houses with the hard water on your faucets, or they get kind of calcium deposits, junk on them. You could clean this off chemically with running some acid through there, but we didn't do that. We just put some new heat exchangers in because this one was kind of getting old and leaking. So next semester, when you go and take UO Lab, you'll get to run some of these shell and tube, this shell and tube heat exchanger setup, not this exact one, but the same apparatus. We just put some new heat exchangers in. So any questions now on some of these types of heat exchangers? We're going to focus mostly on concentric tube and shell and tube. We won't focus too much on brazed plate because we don't often have theories on how to calculate the H's. And in industry, there's some industries that use them a lot, these kind of brazed plate. In fact, if you have a truck, like a half-ton truck, a F-150 or a Chevy Silverado or something like that, they have these types of coolers on their maybe transmission or on their oil coolers or their transmission coolers. Normal cars don't need that because they don't get as hot, but trucks, when they're hauling stuff, they have these kind of, you'll see something like this in the engine of a truck. that's because the oil we put in our trucks is usually very clean. The coolant is very clean. And so we don't get a lot of fouling. In industry, if we're dealing with junk that's coming from crude oil or anything like that, then you have to deal with fouling a lot. These types of heat exchangers would get gummed up very quickly. And so we go to shell and tube heat exchangers because these you can clean much easier. The other thing is they have less pressure drops and they can withstand higher pressures. The others can't withstand as high a pressure. Okay, any questions? I'm gonna bring up the chat right here. See if anyone's got it. Someone's talking about Vulcan and Gryffindor. Good night. I got all these great things to show you, and you're talking about Harry Potter.
Hey, Dr. Nuts, I have a question.
Yeah.
So with the fouling, is that mostly made of like scale?
Yeah, you can call it scale. It's mostly scale. It's just junk that gets deposited on the inside of my pipes or the outside if I'm on the shell side.
So in a typical refinery, are you running the oil through like the shell side or the tube side? The tube side.
That's
right?
a good question. You will run, often you'll run it through both, depending on your application. Because the whole thing about making money with refinery is called heat integration. If we got to heat something up over here, but we already have a hot stream, we're going to take that hot stream, run it through one side of the exchanger, and then put your fluid you're trying to heat up on the other side. Now, having said that, we'll talk a little later about this. You usually put the dirtier stuff on the tube side because it's easier to clean the tubes. Even for this one, I can mechanically put like a big wire scrubber down here, and they're 20 feet long, 30 feet long, kind of like a really big bottle scrubber, like a baby bottle scrubber, and I can mechanically scrape junk off the tube side. So I usually put the cleanest stuff on the tube side, and the dirty stuff on the tube side, and then the cleaner stuff on the shell side. That's also true if I'm doing. It's a little different if I'm doing phase change. So if I'm using steam to heat things up, I want my steam to go on the shell side because it is very clean, and also because I want to form those condensate, those like we talked about chapter 23, those boundary layers over these tubes on the outside. It's a little harder on the inside to get a good film because it would just kind of be, it's horizontal, it's going to be dripping down weird, things like that on the inside. But on the outside, we're better at getting the H's. So mostly steam is almost always on the outside, the shell side. And while I'm sitting here, since I've got this thing, someone tell me why I have baffles from a boundary layer perspective.
Creates turbulence.
Creates turbulence. What if I am condensing?
It just resets your boundary layer, right?
It resets it, right? Because if I didn't have these baffles here, my boundary layer would keep growing all the way the length of this tube, and the fatter it gets, the less heat transfer I have. So by making it reset right here, yeah, I've got to have some water that kind of flows across here and comes down, but I've made the boundary layers reset every time it has a baffle on whatever tubes have the baffle.
Are there baffles through the entirety of the tube, like in the center part too, that connect?
Guys, so usually, and we'll talk about this in a second, if you look at a sphere or a circle, like a cross section, it would just be cut off halfway through. And so you talk about baffle cut. These look like they're about like 60% baffle cut. So if you look at this one right here, you probably can't see it, but it goes all the way through, and then about this much of it is not covering tubes. And then the next one would be a little different, that they offset them so it goes back and forth. But yeah, in fact, well, I have a whole lecture on some of the practical aspects of baffles and things like that in a couple days.
Thank you.
Okay. Let's go to the lecture now. If I can get out of this PowerPoint. Let's see. There we go. Okay. You know, I've debated back and forth. I think I forgot to post the filled notes because I wasn't sure if I wanted to post the filled ones, because most of you, do you want to print them out yourself and make sure you follow along with me? Because I think if I post the filled ones before class, you guys will just not pay attention as much.
I'd rather you post the filled.
I'll post the filled ones. I'll post them right after this. You can take a couple notes on the PDFs. But as you guys know, Learning Suite's a little slow, so I probably shouldn't do it right now.
Dr. Knotts,
Yeah.
with everybody trying to stay in their homes, a lot of people don't have printers.
You guys don't have printers? That's amazing.
We're college kids.
The library has one, but they might close campus anytime now.
No, I'll post the filled ones. Just kind of keep notes. You know how to add a little box with Adobe or whatever favorite PDF thing you're doing. I probably should have posted it today, but I'll make sure to post it right after this. Okay, let's talk first. We already talked about all these different types of heat exchangers. We're going to kind of skip the first part here. How do you design a heat exchanger? You've already been dealing with heat exchangers for some time, all the way back in 273. Probably even in 170, you dealt with some heat exchangers, and you probably drew them something like this, where you just had kind of two rectangles that represent one stream and the other stream, a hot stream and a cold stream, and then you went and analyzed it. So someone tell me, think for a second, someone tell me, what's the energy balance for this heat exchanger? Someone can chime in.
In equals out.
That's true. In, let's see. I don't know, I can't spell today. In equals out. So you got rid of generation and you got rid of, what am I saying? You got rid of generation, you got rid of
accumulation.
Accumulation, thank you, the unsteady state term. You're gonna write, you probably drew something around, here's your boundary, or here's your control volume. So what does this in minus out mean from a practical perspective?
The heat given to the water is the heat that comes out of the oil, or vice versa.
That's right. So here's my hot stream, right? It's hotter. It's coming in at 70. This one's coming in at 27. The heat is going this way. What we're saying when we say in equals out, or that in minus out equals 0, is that all of the heat that's coming out of the oil is going into the water. It's not going to the surroundings. And we usually, that's a good assumption, especially if we put insulation around the outside. And it's even a good assumption if we don't, because the relative magnitudes of the convection that would be coming to the outside out here is pretty small compared to what's happening on the inside. But usually we'll insulate our heat exchangers, or we'll design them with some sort of vacuum or something like that. A vacuum wall. Okay, so I want to make sure I get all my notes here, what I wanted to say. You actually have all the tools you need to design a heat exchanger. Here's what we want to do first. I'm going to call this stream 1 and stream 2 and stream 3 and stream 4. And so if we kind of go back to what we said before, if you remember from your thermo, you probably wrote an energy balance something like this. You wrote nu I m dot I h I equals q plus w. So this is at steady state. This should look familiar to you from thermo, right? And then you said, okay, there's no shaft work going on. There's no heat going on to the outside because we're going to insulate it. We're going to assume it's 0. And so you get, I'm going to write it like this. I'm going to say M2H2 minus M1H1. That is, okay, sorry. We want to do the ins. Let's see. We want to, yeah, that's what I want. M2H2 minus M1H1 minus M4H4 minus plus M3H3 equals 0. Okay, why did I do it like this? Why did I do it like that?
You're summing up all the energy coming in and subtracting all the energy going out.
Yeah, so this is a plus, this is a plus, and so those are the in ones, or sorry, yes, those are the in ones, right? I've actually made those the out. I multiplied everything by a negative, right? Because the ins are the 1 and the 4. What am I doing? Let's make sure I get this. Here's what I'm trying to do. I'm trying to write m.2 and m.1 is just m hot times delta H hot. And m dot cold, this is m cold times delta H cold. So let's make sure that I've got all my signs right.
I think that's supposed to be M1H1 minus M2H2 because stream 1 is coming in and stream 2 is
Yes.
going out.
And then what about over here? 4 is going out. So what I've done is I've multiplied everything by a negative. So let's do like this. Does that make sense now? 2 is coming out. This should be negative. 4 is coming out. 3 is going in, and 2 is going in. So those are the correct ones for the news. But what I'm going to do is I'm going to say this is delta H. So I need a negative sign right here because I usually do H2 minus H1, right? And then this one, let's keep this minus sign here and let's just deal with this. So let's put another minus sign right here. Let's see, 4 minus 3, that's right. That's going to give me a delta H. And so this is going, yes, so this is going to work because one's going to be positive and one's going to be negative. Basically, I get M dot H delta H hot is equal to minus M dot H cold delta H cold. Or Q hot is equal to minus Q cold. It's one of the key design equations, right? Q hot is equal to minus Q cold. And how do I get delta H? This is the easy thing from thermal because these are usually liquids.
MCAT.
Yeah, M dot Cp delta T. Okay. How? Let's see, what other assumptions need to be made? Okay, where am I going to evaluate the heat capacity? Cp cold of what temperature?
Average temperature.
Yeah, the T cold average. Let's do it like that. You evaluate the heat capacity at the T cold average, the heat capacity of the hot stream at the T hot average. What if you don't know the temperatures out? What are you
Probably
gonna
have
do?
to use a solver.
Yep, you'll have to use a solver, right? So what I can do initially, right, is I could guess a T cold out and a T hot out. So I could guess to get this. And then I could solve it out and then iterate, or I could stick it all in a solver. What else do I need to specify to finish this up? I need to specify like an M dot, right? M dot cold, M dot hot. I'll have to give you those, or you have to specify those. And then you'd also, and then that's about everything we're gonna need to specify. Now, so those are 3 of the key things. Q cold is equal to minus Q hot. That means all the Q coming out of the cold is going into the hot. Q from thermo is M dot Cp delta T. And I can write one of those equations for the hot side and one equation for the cold side. There's one other equation we've learned about. So I'm going to rewrite these. Q cold is equal to M dot cold, Cp cold, T cold out minus T cold in. The out on the cold side will be hotter than the out on the inside, so everything will be positive right here. Q hot is equal to M dot hot, Cp hot, T hot in minus T hot out. Hot in will be hotter than hot out. You might need to think about that. And so all that'll be positive. And then the other equation we have is Q cold equal to Q hot also equals UA delta T log mean. You've done all this stuff before in thermo and in 273 and things like that. You learned about this one in this class. You just took a test on stuff like that. At least I think one of your problems had. Now, delta T log mean, you've already seen. Here's the definition of it. Let's talk about counter versus co-current now, though, with delta T log mean. An important concept. Got to make sure we get settled because it changes depending on whether it is hot or cold. Remember, when I write delta T2, that corresponds to a specific position in space, not the out or in. That's the way you want to think about this. And when I write 1, I'm referring to a specific position in space. So here's the 1, here's the 2. If you always think about it like that, this side of my heat exchanger and this side of my heat exchanger, you'll be able to write your delta T log mean right. Because for counter current, I'm going to have, say, T hot in and T hot out and T cold in. The ins are going to be the opposite sides of each other. That's what I mean by counter current, anti-parallel. You'll hear both those terms. So the hot, the in, and the in for both streams are on opposite sides, physical sides of the heat exchanger. So if I'm looking at this heat exchanger, I could make this counter current by putting hot in right here and cold in right here. Opposite sides, physical sides of the heat exchanger. Co-current, I put the inlets and the outlets on the same side. So T hot in, T cold in, T hot out, T cold out. And if I remember that, then I can say T1 is equal to T hot in minus T cold out. And then T2 is T hot out minus T cold in. And then this one is T hot in minus T cold out. And this is T hot out minus T cold out. I do not try to memorize these of counter versus co. What I memorize is I literally just draw something that looks like this, put a 1 in and a 2 in, and I remember this is its space. It's describing the driving force, right, at every X position along here. It's at space. So it's T1 side, where 1 refers to a side of the heat exchanger. And so if it's counter current, then I would have a hot here, hot in, and cold out. If it's co-current or parallel, then it would be hot in, cold in. And that would be my T1. And then I'd go over here to get T2. That is where students mess up the most when they're trying to do their delta T log means. Don't try to memorize these. As in, don't memorize this thing and this thing. You're going to mess yourself up. Is it a hot in? Is it a cold in? Is it a hot out? Is it a cold out? Just draw it out, little simple diagrams just like this, and then you won't mess up.
So Dr. Knox?
Yeah.
It looks like, so your delta T1 on the bottom, should that be T hot in minus T cold in?
Oh, you're right. I wrote that wrong. Sorry.
Okay, just making sure.
Yep. Everyone saw that right here. I changed that to an I. But once you get that right, you guys know how to design a heat exchanger now. You have these 3 equations, and all of those can be used in any combination you want, depending on the number of unknowns you have. Now, let's just want to check the time real quick. There's a couple other things I just want to make sure that you see in the book. The book does a little nomenclature called capital C, little c, and I try to really emphasize that because it's hard to tell C's apart. M dot cold, CP cold. They just combine the M dot and the CP for some reason and call it something capital C, and they do something similar for the hot stream. I just want to make you aware of that in the book. They have some fancy name for it. I can't remember what it is, but it's there. Okay, I want to get to the example here. But before that, we got to do one other thing. How do we deal with this fouling? What I've shown you here is a diagram of, say, one tube. So I've got an inside, I've got a tube thickness, and then I've got an outside diameter, and then I've got what would be happening, the T infinity on the outside. So this is just a normal pipe or a tube. It could be one of the tubes inside here. And all these tubes have an inside diameter, an outside diameter. And so I have an H inside, I have an H outside, and I have a wall thickness. And then if I have fouling, then I'll also have other junk. And so what do I mean by fouling? If I, notice here that I kind of just blew up this section of the pipe. And so this is inside, and I would have an H inside, and the resistance would be 1 over H inside, area inside, and which is 1 over H inside pi d inside L, where L would be the length of the tube. So we've already done that lots of different times. On the outside, I would have 1 over H outside, area outside. 1 over H outside, which would be pi d outside times L. Any problems with that? Just normal convective resistances. I'm looking for the inside of the pipe, then I'll have a conduction. The conduction right here would be log R2 over R1, 2 pi KL. Normal cylindrical resistance. Convection, conduction, convection. If I had some fouling, usually it's going to be on the inside of the tubes if I've designed it right, then it's like I had a little film of junk that built up right here. And the way I'm going to deal with that is I'm going to say I'm going to just call it something called RF double prime. And in this case, it would be over area inside. I could theoretically have one on the outside too, right? I could have junk build up on the outside, and then I could also have an we'll call this the outside fouling factor over the area outside. We'll call this
Dr.
one
Knopf.
the inside. So theoretically, I can have fouling factors on both sides. Usually what we do is we just lump them together because we don't have enough information to solve them independently. But let's sum up these resistances now, right? I've got convection, fouling, conduction, fouling, convection. And that's what you see here. The total resistance, which is related to 1 over UA, is convection on the inside, fouling on the inside, conduction through the tube, fouling on the outside, and then convection on the outside. So all we've done to account for fouling is we put in this term called fouling factor. If we knew its thickness, right? If we knew this thickness, look up here, if we knew this thickness and we knew the thermal conductivity, then we could just calculate it as another conduction resistance. But we often don't know that. We don't know how thick it is, and we don't know what it's made of. And so we just call it this factor. And when we're designing, usually we'll just assume some sort of average value. But because it's a resistance, it's fairly easy for you guys to calculate. It's kind of like a contact resistance when we're doing conduction between two solids. It's just a number I stick in there. Now, there's a few things we want to notice about this UA. Notice that I've written UA without any subscripts. Let's actually go back up here. I wrote it without any subscripts here. And then I put it, the book also does this. I could call it based on the inside or based on the outside. All this is trying to show you is that we usually talk about UA as a whole, not just U separate from A. And the reason is, if I expand out the areas, notice that here's my area inside, 2 pi r or pi d times L. Here's my area inside. There's no area per se here, right? The area is part in this log and part in the L. And then here's my area outside and my area outside. So I really can't separate the area out, right? Because one of them is the inside and one of them is the outside, and one of the terms doesn't really have the area. Now I can kind of hack it. Like if I wanted to divide everything by, say, or if I wanted to multiply everything by area inside, I could do that. And what it comes out to be, though, is I have to stick some r's in certain places, right? Because I have to multiply by 2 pi r inside L. That would cancel out this term, and so I just get an H. It would cancel out this term, so I just get a 1. But here, the 2 and the pi would cancel out, but I have this extra r that has to get put in there, and the L would cancel out. Do you see what's going on here? And then here, the 2, the pi, the L would cancel out, so I get this R over R, and the same thing here with this R over R. So I can write it in terms of a specific area if I want, but it kind of messes up your concept of resistances. What I usually do is I just think this, UA, is some of the resistances, and I just think of UA as one thing, not a U times an A. Okay, someone tell me if you're confused by this.
Dr. Knotts, I just had one question, and maybe you answered it and I just missed
Dr.
it.
Knotts, I have a question on it real quick.
Okay, wait 1 second. Someone was going
For
first.
yeah, for the conduction resistance, you have an ln d naught over di. Why are those diameters not radii?
Right here.
Yeah.
So that's the same, right? D naught over D inside is the same as R over R
it'd be the
outside
same
because
ratio.
there's just a
Okay.
2 right here.
Yeah, that makes sense. So it's the same ratio, but
It's
okay,
the same
cool.
ratio. Sometimes you'll see D's, sometimes you'll see R's.
Okay, that does make sense. Thank you.
What was the other question? Was it Connor?
No, it was me.
Okay.
Yeah, sorry for speaking over the other guy. I couldn't hear him talking. My
That's
volume
okay.
was down. But my question is, for that 1 over UI, where you've multiplied the area through, isn't the area of the inside different? So how does it come out? That's confusing.
So yeah,
to
if
me.
I multiply by area inside, it looks like this on this line, the red, then it would get rid of this area. And so I just get an H. It would get rid of this area, so I just get this 1. But it doesn't get rid of everything in this term. Let me use green here. In this green term. And I get this R.
Oh, okay, I see it.
And then
Oh,
same
I
thing
see.
here and same thing here. That's the point, is I usually don't think of U separate from A because I think it kind of gets messy.
Okay, that makes sense. Thank you.
And then just one more thing. We've used one approximation and the book uses it. We won't use it for any real calculations, but for simple things, maybe even for a final exam. If I say something to be thin walled, if the pipe wall is assumed to be thin, what does that mean? That means that area inside equals area outside, and that log D outside over D inside over 2 pi KL is negligible, and there's no fouling. And we should put no fouling. And what's that allow me to do? It allows me to separate out U, so it's just 1 over H inside. Sorry, we need another one here. U would be 1 over H inside plus 1 over H outside. And I could separate out the area, basically. And it's just one area. So thin-walled just makes it so that all the areas are the same and I don't have conduction. It's just to practice so that it simplifies some of the calculations. But we've kind of already dealt with that before. Okay, I want to spend the last few minutes talking about an example. You got a counterflow concentric tube heat exchanger. I give you a temperature, T in, T out. You're heating water. So cold, water is cold, is the cold stream. And then this is a concentric tube. So remember, a concentric tube, if I give you the cross section, is a tube within a tube. And then we're using hot oil in the annulus, which is this part, to go from 160 to 140. So this is the hot fluid. The oil is hot. And notice the only things I give you T's, and I give you a U in this case, and I give you Q. And I'm asking you to find the length. And then we'll do part B in a second. So can you find the length? And here's a little diagram of it. Let's just double check a few things. Countercurrent. Is it countercurrent? I'm going to draw 1. I'm going to draw 2. Countercurrent means the in and the out are on opposite sides. So this is T cold in. This is T cold out. This is T hot in and T hot out. I draw them out just like this to make sure that when I do my delta T log mean, delta T1 will equal T hot out minus T cold in, and delta T2 will equal T cold out minus T hot in. And actually, I'm gonna rewrite this. It's T hot in. I want them all to be positive. You can have them all positive or all negative. Just make sure they're all consistent. Remember, it's position in space. It's not in minus out. Remember that, not in minus out for this when we're talking about delta T log mean. It is in minus out when you do Q is equal to M dot CP delta T. That is in minus out. Make sure you keep those separate. Okay, how are we gonna solve this out? Well, let's see if I've got this written down somewhere. We've got these equations, right? These are my design equations. I can write one of this for the hot side. I can write one for the cold side. And then I've got my heat and mass equation, delta T log mean. I only have two unknowns in this case, and so I don't need to write all three of the equations. We'll get to that in a second. And then also note that I say thin-walled, and so I kind of already talked about this above. The areas are the same, and that our conduction goes to 0. And so that means that U is equal to 1 over H inside, H outside. Oh, I think I have it written down right there. Okay.
Dr. Knotts, if it's thin-walled, we cannot then have fouling, or could you still have
if it's
fouling
thin-walled,
even-
there's no reason. You won't have fouling. Just assume you're not going to have thin-walled in real life. But right now, I'm not assuming fouling.
Okay.
In fact, for this problem, I specifically kind of say I think it's new. I just get this new heat exchanger, and then I say after 3 years, it does have fouling. Okay. And so we'll see how to deal with that. You will know if I give you a fouling factor, you use fouling. If I don't, you assume it's 0. Okay, so the first thing was solve for L. I can solve for L just from the normal Q is equal to UA delta T log mean. Delta T log mean. And this is pi times D times L, delta T log mean. I have what I need to have all the temperatures to calculate this. I'm given this, and I'm given this. So I can just solve for L fairly easily. That's what you get here. It's about 1 meter long, 0.96. Okay, that's the easy one. Now I say after 3 years, the heat transfer's gone down. Now the outlet temperature for one of the streams is reduced. I can't remember what it's reduced to. It says, oh, I've got the notes up
Dr.
here.
Knotts, is there supposed to be an L in that denominator?
Did I forget an L? Oh, man, I had that in my notes. I forgot to write that in. This is wrong. This is a typo. Thanks. Was that Connor? I think that was Connor.
Gives me extra credit. Yes, it was.
You guys don't need extra credit.
After last exam.
Okay, so I think the T hot in and the T cold in are the same now, but we said after some time, what did we say? The water outlet's only 65 instead of 80. Now it's only 65. The T hot, that would be T. Did we do water's the cold? Let me put cold right here. Cold, T cold out, and T hot in. Okay. Now you'll notice there's a lot of stuff I don't know here. I don't know what T hot out is. And I don't know what U is anymore. Right? Because the heat transfer's gone down. There's junk on there. There's a fouling factor. I don't know what U is. So the first thing I need to do is figure out T hot, and then I can figure out fouling factor. And the way I can, someone tell me how we can figure out T hot. What equation can we use? Well, I got it right there. I know that Q cold is equal to minus Q hot. in the sense that everything comes out of the cold, goes into the hot stream. And so I know everything about the water. I know the m dot, I can get the CP, I know the delta T. So I can just rearrange to get the m dots. I'm going to get the m dot of the cold stream, which is before and the same after the 3 years. I'm going to get the solve for the new Q. So here is my new T average. Here's my new T. That's what the N means, new. Here's my initial, or my T cold. So this is all just m dot CP delta T. Just using my new Q. So remember, before it was 3,000. And now we are at 2250-ish. Okay. How am I going to get my new U? Because that's how I'm going to get fouling factor. Well, I need to calculate m dot again for the hot stream because I didn't have that, and you'll see why in a second. This is just m dot CP delta T. That's my m dot hot. The oil, I don't really need to flow that much to heat it up because it's got so much thermal mass in there. And now, this was with all my old stuff, right? My initial conditions. Now I have a new T, but notice here, I need to solve for an F solve because that T hot out new, let me write it like this. Is in multiple places, right? Because I have to evaluate the heat capacity at T average. And then this is the T hot in minus T hot out part of m dot CP delta T. But I can stick that in an F solve and I get something like 418. And once I have the new T, I can calculate a new U. Here's my delta T log mean. We already talked about delta T1, delta T2, delta T log mean. Comes out to be like 109. And then I just use Q equal UA delta T log mean, solve for the new U. Why do I want the new U? To determine my fouling factor, look at this little mathematics here. Here's what U equals without fouling. Here's what U equals with fouling. And so if you go through the math, I can just subtract 1 over U new minus 1 over U to get my fouling factor. And I want to end with this. This is pretty significant. What is the value? Notice the value here. You don't need to say it is, but it's like 10 to the minus 4. And typical fouling factors maybe go from 10 to the minus 3 to 10 to the minus 5. Of course, if you go to 0, then it would be assuming no fouling. This is very high. You need to probably clean your heat exchanger if you're into the 10 minus 3 range. And 10 to the minus 4 is probably okay. Also notice the units, it's in terms of resistance. Kelvin's on the top, meter squared on the top, watts on the bottom. So what are you doing for your homework? And then we'll sign off. I know we're a couple minutes over. You have a problem similar to this. You have a concentric tube heat exchanger, and you need to calculate I give you the T-ins, and I give you the flow rates, and then I say calculate the T-outs. But I don't give you U. How are you going to get U? And that's the question you got here. And it's kind of the same question twice. I gave you U in this case, but what if U is unknown? How do you calculate U? Someone raise your hand and tell me, or just chime in. Anybody? I should do this one for extra credit.
Isn't it the sum of all the resistances?
Okay, so how are you going to get that H inside?
A Nusselt number correlation?
Yep, Nusselt number correlation. And then you'll have something like a log R2 over R1, 2 pi KL, that's the easy one. How would I get this 1 over H outside area outside, where this is now in that annulus?
That would just be another new salt one, wouldn't it?
Yes, there's new. Go to chapter 8. It talks about how to do this for annulus, for the annular region.
So we don't assume that it's like flowing perpendicular over a cylinder for that one.
No, it's not perpendicular over cylinder, right? Because it's going lengthwise in the cylinder like this. It's not going crosswise. This is in chapter 8, and you'll be able to see it pretty easily. It shows you a picture of a concentric tube or a pipe in a pipe, and it'll tell you how to get the H. Okay. That is what we got for lecture today. Your homework's posted, your key, the template's posted, and I hope that you do well. Don't forget, I have office hours, and to help out, I'm gonna do office hours every day at 11, at least for the next couple of times, at least this week. Today, Thursday, Friday. I wanna help you make sure you got time for your homework, get all the help. The TAs are doing things by Zoom, and so if you have questions, make sure you get on. No one came on today. That's probably because you didn't have any questions. Either you had the exam going on or you had no homework, so you didn't have any questions. But make sure you try this and ask me any questions you need.
So wait, you're gonna have TA hour or office hours every day this week?
Yeah, so I'll have it. Well, I had it today, but I'll have it tomorrow at 11 and on Friday at 11, like normal.
All right.
Any other questions?
Dr. Knotts, I have a quick question.
Yeah.
For our homework, once we have the U factor, after finding our H's through the Nusselt correlations and whatnot, how do we actually get the T outs from there?
You have 3 equations, right, that you can use. You have Q is equal to UA delta T log mean, and so T outs are inside here.
Right.
You also know that Q is equal to M dot CP delta T, and you can write this for the cold side or the hot side. And so you're going to have probably 2 equations, 2 unknowns, but your 2 unknowns would be T cold out and T hot out, and you can do these 2 equations to get them. Or you could write Q hot, right? It will give you all the same, or you could use the hot one to check your answers. If I get the T's from here and put it in here, then I should be able to get the right Q back out. And so you have up to 3 equations that you can write there, 3 equations, 3 unknowns. But on this problem, I think you only have 2 unknowns, basically, right? You
Okay,
don't
that
know
makes
what
sense.
the T outs are. Any other questions before we sign off?
Will the neutral number also be dependent on the temperature? Because
It will. You guys know how to deal with that nowadays, right?
Right,
What do you do?
okay.
Reynolds number, a function of T out, and then you can have Nusselt number, function of T out, and H, a function of T out. And so it's still just, you use functions inside of your given blocks, or not given block, inside of your F solves. I think I give you that hint too, just make everything functions of T out. I even give you the answers since we're doing this remotely so that you can check your answers compared to what I got if you look at the homework. Anything else? Okay, I'll be on at 11 tomorrow. I'll be on 11 Friday, and we'll keep going with heat exchangers. You're going to get a lot of practice with heat exchangers. And so it doesn't get really much harder than this in the rest of the class, but we teach you another method to do it that you need to be aware of. So you want to make sure you come next time. It's called the epsilon NTU method. You have no clue what that means. It doesn't even make sense, but you can just show up. But make sure you get started on this homework. So if you get stuck, you can get help from me or the TAs.
Dr. Knotts?
Yeah.
Do you have hours every day at 11, or just this week, or?
For this week, I'll do it, and we'll see how it goes tomorrow. So I'll come in tomorrow at 11. I'll come in Friday at 11. Into
Okay,
Zoom.
and then we'll go from there and see if you do it more.
Yep.
Okay, cool.
Okay. Good luck. And you can email me too if you have questions. And the TAs, I got to go post the key right now, so the TAs are ready, but they have it, but because I forgot to post it. But I'll also post the filled notes. Thanks, everyone. Stay healthy.